Hi everybody, welcome back to my channel. Today we're going to look at contactors. I've got a bunch of them here, some newer ones, some really old ones, and I want to show you exactly what goes on inside of a contactor. That's what we do here. We carefully disassemble things to show you their inner workings, and then never quite get around to putting them back together. A contactor is a remote switching device that pretty much does the same thing as a relay, except for it's generally rated to handle much higher loads, and they have some unique features. Their most common application is to run electric motors, so that's what we'll be doing here. This is an old school reversing contactor, so it's basically two identical contactors interlocked together on a single frame. One side is to run the motor clockwise, and the other side is for counterclockwise. But forget about the one on the right for now. Let's just pretend we have a single contactor. It has a 24 volt AC coil, like most of them do, which pushes or pulls together the high voltage contacts, allowing current to flow to the motor. This one has 3 poles. It's like having 3 separate switches that are all activated by that 24 volt coil. These poles are all independent of each other, so you could use them for 3 separate circuits with 3 totally different voltages. But most of the time, they're all used together to run a single motor. And any voltage you send through the main contacts is going to be isolated from the coil, so you don't have to worry about the high voltage mixing with the low voltage circuit. So here's a more modern contactor with 2 coils and 2 sets of contacts. This one side with 1 coil is a contactor. This is what you would have for a motor that only needs to run in one direction, like a compressor. 2 contactors joined together with an interlocking device make this a reversing contactor for motors that need to run in both directions. Right now we're just going to use one side of it to run this 3-phase induction motor in one direction. I'm going to connect 24 volts to the coil terminals labeled A1 and A2 with a push button to start and stop it. Polarity on the coil terminals doesn't really matter. I'm going to bring my 3 phases from the breaker panel into the terminals labeled line 1, 2, and 3. Now we have constant power coming into the contactor, and when I connect 24 volts to the coil, it will allow that power to go through the main contacts to terminals T1, T2, and T3. I don't know what T stands for, but I know it gets hooked up to the load. And there you have it. I can use a cheesy little single pole switch that's only rated for 1/4 of an amp to run a 3-phase 460 volt motor that runs at 20 amps. Here's the schematic for what we've done so far. We have the 24 volt coil with terminals A1 and A2. We have our 24 volt power supply and a switch to make or break the power to the coil. This is our constant 460 volts from the building power in 3 phases. This is the motor with its 3 terminals, and these are the 3 poles of the contactor that will open and close together when the coil is energized. This dashed line represents the magnetic force from the coil that pulls the contacts closed. So when I energize the coil by pressing the push button, it closes the main contacts and connects lines 1, 2, and 3 to the motor's 3 windings labeled 1, 2, and 3 respectively. If I were to swap any 2 of the 3 phases, the motor would run in the other direction. That's where the other contactor comes into play. The first one will be our clockwise contactor, and the second one will be our counterclockwise contactor. So here's our 2 contactors, each with their own button to send 24 volts to their individual coils. The original clockwise contactor is hooked up just like we had it. The counterclockwise contactor is going to get 460 volts from the same source as the other one, and the load side is going to get connected to the same motor but with phases 2 and 3 swapped. So there's always voltage present at the line side of each contactor, but you can only operate one contactor at a time. So whichever set of contacts you close will determine the path of the current to the motor and the direction it spins. Since there's always constant power coming into the line side of the first contactor, I just ran jumpers from those terminals to the line terminals on the second contactor. This takes up a lot less wire than going all the way back to the 3-phase power source. And again, on the load side, instead of running wire all the way to the motor, which might be, 20 feet away from the contactor, I'll just run jumpers from the load terminals on the first contactor. Now it looks pretty complicated, a lot like the tangled web of wires you see inside these machines. But if you just look at the first contactor and ignore all the jumpers, you can see that when the coil is energized, the 3 wires from the power supply go straight to the motor terminals. For the other direction, it's much easier to imagine that the clockwise contactor doesn't even exist, and that there's just some terminals that connect the wires together. And when I spread it out, it hopefully makes even more sense. You've got your 3 phases coming into lines 1, 2, and 3, and then they come out and go directly to the motor, but with 2 and 3 swapped. Some of these reversing contactors come with jumpers built right into them from the factory, and it's going to have 2 of the poles already swapped on one of the contactors. That phase swapping can happen on the load side or the line side, it doesn't matter, and usually they make it so you can remove those jumpers if you need to. Now, of course, you never want to energize both sides of the contactor at the same time. If you try to run a motor both directions at once, it's either going to blow the breaker or make a weird sound and eventually let the smoke out. These reversing contactors have interlock devices to prevent that, which we'll look at in just a second. So why do we even need a contactor when we could just use a heavy-duty 3-pole switch? There's a lot of reasons. Most of the time, the signal telling the motor to run goes through a bunch of different switches and sensors and stuff, and those components usually aren't rated for the kind of current the motor draws. So it can be a lot more economical and less cumbersome to have a low voltage control circuit with less expensive single pole switches and stuff. The same goes for the wiring. This button might be located 100 feet away from the motor, and 100 feet of 18 gauge copper wire is a lot cheaper than 100 feet of 12 gauge wire. Another reason is safety. You don't necessarily want 230 or 460 volts running through the user interface, where it could short out and electrify the enclosure. And when it comes to industrial motors, you need a reliable, fast-acting switching device to minimize arcing. When these contacts get within about a millimeter of each other, the current will jump from one contact to the other, and that develops a lot of heat, which will eventually ruin the contact surfaces. So the faster you can engage the contacts, the less time they spend arcing. Generally, switches with a higher load capacity make a bigger clunk. So how about those interlocks? Like I said, it's really bad to try and run a motor both directions at once, and it only takes a few seconds to ruin a motor. So these contactors all have mechanical interlocks that kind of work like a seesaw. They make it impossible for both sides to pull in at the same time. As another layer of protection, they might also be electrically interlocked. The right side of this contactor has a normally closed switch that opens whenever the coil pulls in. The 24 volts that activate the left side coil go through this switch. So whenever the right side of the contactor is pulled in, it interrupts any voltage going to the left side coil. There's one of these interlock switches for each coil. Here's a single contactor. It looks like it has an awful lot of terminals, but that's because it has a spare connection point for each terminal. It has the two 24-volt coil terminals labeled A1 and A2. It has the line side terminals for the 3 poles labeled L1, L2, and L3, and it has the load side terminals T1, T2, and T3. This one, like most of the new ones, has a fourth pole labeled NO for normally open. It works just like the other three poles, but it's not always rated for the same current as the other poles, so you do have to be careful. This fourth set of contacts is usually used for something in the low voltage circuit. Here's another identical contactor, and they're made to be joined together with this interlocking module to make one reversing contactor. The interlock device has these little tabs that can only be moved individually. The tabs fit into the contactors and physically prevent both sides from being pulled in at the same time. It also has two normally closed switches built into it that work as the electrical interlocks, one for each side. So just like on the old contactor, you would run one of the 24 volt coil leads through the appropriate interlock switch and then to the coil. That fourth set of contacts, the ones labeled normally open, are a lot of times used for continuous operation with only momentary contact of the push button. That means the contactor stays pulled in after you let go of the button or whatever. Constant contact means having to constantly hold in the button to keep the motor running. To switch over to momentary contact, I'm going to use that fourth set of contacts in parallel with the 24 volt push button to make that contactor function like a latching relay. I need a constant 24 volts to go into one of the normally open contacts, and I might as well get it from in front of the push button. Then I'm going to run a wire out of the normally open contact and to the A1 terminal of the coil, the same place the wire from the push button goes. So right now there's no power going to the coil. When I press the push button, it sends 24 volts to the coil like normal, pulls in the contacts, and the motor runs. When the contacts close, that normally open contact, that fourth pole, also closes. So A1 is getting its 24 volts through two different paths. When I let go of the push button, A1 is still getting 24 volts from the fourth set of contacts, so the coil is still getting power and the motor stays running, until that 24 volts is interrupted by something like a limit switch or a stop button, which would be a normally closed switch somewhere in series before the push button. And if the power went out while this motor was running, it wouldn't start back up when the power was restored. You would have to restart it by pressing the push button. This way you don't have a bunch of machines all fire up at the same time when the power comes back on. That's it for now. If you like this video, then I have all kinds of other stuff just like it on my channel, so you might want to check it out.